Welcome to the MGH brain-PBM clinic rounds. I'm Paolo Cassano. Today is March 8, 2024. It's my great pleasure to introduce Dr. DaeKeun, who is the director of the R&D at iMediSync and who is going to discuss today the use of QEEG-guided PBM. Dave, welcome, and please take it away.
Okay. Thank you for inviting me this very important group, and it is my honor to present today. I'd like to share my screen first. Yes. My name is DaeKeun Kim, simply Dave Kim. I'm the director of the iMediSync R&D Center. My presentation today is about real-time changes and intervention effect of QEEG-guided pulse transcranial PBM, how pulse frequency can affect EEG changes. I'd like to briefly introduce myself. I studied electronic engineering at KAIST and Seoul National University and emotional engineering at Sangmyeong University. I'm currently director of R&D Center, iMediSync, company that provide QEEG-guided AI mental health platform services. For 8 years from 2012, I built the world's first sex-classified QEEG health normative database through National Reference Database Project. And since 2016, I developed FDA-approved iSync brain software platform that automatically analyze EEG using AI technology. In 2020, I developed iSync Wave, FDA-approved 19-channel dry EEG headset with photobiomodulation function. And now I am currently continuing my research to spread precision psychiatry and neuromodulation using QEEG. Today's the first part of my presentation introduced the concept of QEEG-guided pulse transcranial PBM, and in the second part, I will introduce real-time EEG effect during continuous near-infrared tPBM. The third part, the real-time EEG effect during pulse near-infrared tPBM. Finally, I add the intervention effect of QEEG-guided pulse tPBM. The first part, the QEEG-guided introduction of the QEEG-guided pulse tPBM. While the investment in neuropharma is stagnant, the market for neuromodulation continues to expand. Neuromodulation include a variety of physical stimulation methods, including transcranial electrical stimulation, TMS, TENS, ECT. Neurofeedback actually does not provide external physical stimulation, but use our own intention to change our brain wave. Among many other neuromodulation, TMS, TDCS, THS have been in the spotlight, but tPBM has recently gained attention. Today, I'm going to talk about how iMedicine I work for uses this neuromodulation technique in conjunction with QEEG to maximize their efficacy, especially in the tPBM area. I will start with brief introduction of the AI mental health platform I have I have built in iMediSync. Let me briefly explain the structure of how iMediSync provides QEEG-guided tPBM on AI platform. iMediSync developed the FDA-cleared EEG dry headset that enables simple EEG measurement and measure the signal automatically calculated by EEG analysis software, iSync Brain, in the cloud and compared to health normative database. And then result of the EEG, based on the result of the QEEG analysis, photobiomodulation stimulation suitable for each individual QEEG profile can be prescribed and implemented by the using the cloud interface. For example, the remote expert can prescribe PBM for the user anywhere in the world. That's the basic AI platform service from measurement and analysis and the QEEG-guided tPBM using the simple headset. We have two different PBM devices. Basically, this device is the first device we developed. This is the second device we developed. The second device called iSync Me is more lighter and more stretchable. The size is smaller, but more stretchable. So even very young children under 6 years old can record their EEG using this small headset. So that's our QEEG-guided PBM device. And I'd like to briefly explain the basic mechanism of the first tPBM. There are two different mechanisms I'd like to briefly talk here. The first one is the right penetrating the skull, activate the cytochrome C oxidase in mitochondria. This stimulate ATP production and NO production, which improve blood circulation and improve many protein transcription factor, and angiogenesis, synaptogenesis are increased, and neurotropins are increased, antioxidant process are improved, immunity is improved. This is very well known photobiomodulation mechanism. Another important mechanism is the right-gated ion channel, as you can see here, right-gated ion channel, which may explain the frequency in training phenomenon. I'd like to focus today the entrainment phenomenon by the first frequency photobiomodulation. The wavelengths we use in our device is 850 nanometers. 850 nanometers. We can take advantage of both mitochondrial activation and also the right-gated ion channel. And the brainwave basically created by the synchronized activity of many neurons, and neurons that are synchronized by a right pressing at a certain frequency are expected to produce the brainwave rhythm of that flickering frequency. That's the entrainment. Many people use the continuous PBM, but the first frequency PBM is another important PBM mechanism, I think. I'd like to briefly explain the hypothesis that create the rhythm in the EEG called macro-column resonance. The column is the subsculpt structure with a pyramidal cell aligned in a very specific direction as shown in the figure. The theory is that when the nearby columns are synchronized, fast rhythm like beta are created. And when distant columns are synchronized, slow rhythm like alpha are created. Just as the SA node is the pacemaker of the heart and regulating the rhythm of the heartbeat, in the brain, thalamus is the pacemaker of information processing in the brain, synchronizing cortical area with pathway from the thalamus to the cortical area and to the back to the thalamus again to create alpha rhythm. This is a very long connection. If we stimulate the neural tissue in particular area at a certain frequency, that area, the area that synchronized to that frequency will be produce a corresponding brainwave rhythm, just as thalamus synchronize entire area to make an alpha frequency. So right stimulation can be another pacemaker that synchronize those areas to produce EEG rhythm that correspond to that frequency. That is basic idea of entrainment. Let's take a moment to look at the entrainment in different neuromodulation. Here we have TDCS and TACS. TDCS, very famous, recently has been used to treat depression, does not show entrainment because it used direct current, not pulsed current, pulsed current to modulate. The TDCS modulate the firing threshold of action potential. So it does not make the entrainment. Just modulate the firing threshold of action potential. But TACS, however, is known to show entrainment as shown in the figure. We can use the frequency of TACS to speed up or slow down the EEG in the specific area. This is the entrainment in TACS. And this is the entrainment in the TMS area. This study replicated the hypothesis that the stimulation frequency used in depression RTMS study would maximize effectiveness when we select the stimulation frequency according to the individual alpha frequency. Usually 10 Hz RTMS is commonly used. It has been shown that antidepressive effects are greatest at frequency slightly lower than 10 Hz. But the decreasing effectiveness as the frequency move away from this. Using RTMS frequency slightly faster than individual alpha frequency of the depression patient was superior to stimulation at 10 Hz in all cases. For example, 10 Hz RTMS may be greatest efficacy for depression patient and the patient having the alpha frequency of 9.5, for example. But 9 Hz RTMS is more give us a better better efficacy when the people having the 8 Hz alpha peak frequency. People have 7 Hz alpha peak frequency, 8 Hz RTMS give us the maximized frequency. So this replication study shows individual alpha peak frequency. We can select the RTMS frequency based on individual alpha peak frequency to maximize the efficacy. For example, 7 Hz alpha RTMS frequency, 8 Hz is the best frequency. But in this case, they use the 10 Hz alpha RTMS stimulation frequency. So just 9 Hz frequency give the maximum efficacy. So this is the tuning effect of the entrainment. The 9 Hz frequency is more likely to tune the 10 Hz RTMS. That's another kind of entrainment in RTMS area. There's another form of entrainment called audio-visual entrainment. On the left, the audio entrainment device, recently produced by a big Korean electronic company. It uses binaural beat to introduce specific frequency, which is different entrainment rhythm, entrainment mechanism. On the right is a picture of the visual entrainment. Visual stimulus of a specific frequency induce that frequency in the visual cortex EEG rhythm. Visual cortex in the occipital area turn on and off at a certain frequency of light, creating a synchronized rhythm of that frequency. The most important thing here, not just in RTMS, THCS, audio-visual entrainment, but also in transcranial photobiomodulation, most important thing is determine which frequency is optimum for specific person and which area are needed to be a target. That's the very important parameter for the intervention. On this page, I will summarize I will briefly give you the recent study that have reported EEG changes when continuous or pulsed tPBM are applied. In the Jomorodi study, 40 Hz was used. They found slow wave decreased and alpha, beta, gamma are increased. And Jahan and Spera study using continuous PBM showed the decrease in delta and increase in beta, which is similar to our study, which showed increase in beta 3 and gamma when we use the continuous PBM. And for the pulsed PBM, Yao's study using 5 Hz, 10 Hz, 20 Hz found that they found faster stimulation frequency shifted EEG frequency distribution toward the faster direction. This is another tuning or entraining effect. And while the 40 Hz and 100 Hz improved cognitive performance and increased gamma in Tang's study. This was similarly observed in our study using 10 Hz, 20 Hz, 40 Hz stimulation, whereas we found specific stimulation frequency tend to increase the EEG rhythm in those frequency bands. So in summary, it can be assumed that continuous PBM speed up the brain waves, while pulsed PBM enhance EEG in the stimulation frequency band, not just in the beta and gamma, but also in the alpha. Let's break this down in a bit more detail in the next part. In this second part, I'd like to review the EEG changes during real-time EEG changes during the continuous transcranial PBM using the infrared light. Here is the experiment overview. The continuous PBM target is the frontal area, measuring 2.5 minutes at baseline. That this is the target of the PBM, and this is our device. And we can record EEG at the baseline and during the stimulation, and another after the stimulation, we measure the remaining effect. The 2.5 minute baseline and 10 minute stimulation or sham stimulation from S1 to S4. After 10 minutes, remaining effect is measured again, another 2.5 minutes. This is our study table. There were 12 sessions of the real PBM, another 12 sessions of sham PBM, and we can compare. The entire 15 minutes of the raw data was bandpass filtered and common average reference and adaptive mixer independent component analysis to make a clean data. And the statistical analysis was performed on the 12 PBM session data in each slot, plot free S1, S2, S4, S3, S4, S4, and 4, and another 12 sham data for each time window. We can compare together or make a statistical analysis. In the delta band, you can see this is the 1, 2, 3, 4, 5, 6. Is this the baseline? S1 stimulation 1, stimulation 2, stimulation 3, 4. This is a 10-minute stimulation and another post measurement. And compared to the baseline, you can see the delta band at the frontal area tends to decrease in the in the frontal during the this is the frontal area. This is central, temporal, perioccipital. You can see the delta tend to decrease a little bit in the frontal area during the PBM compared to the sham. You can find this kind of significant decrease area in this p-value chart. This is S1, S2, 3, 4, and post compared to the baseline. Okay. And the theta band, as you can see, the frontal theta tend to decrease. This is the PBM, this is the sham, and compared to the sham PBM, real PBM decrease in theta decrease, tend to decrease during the stimulation. And you can also see this is the frontal stimulation area tend to decrease significantly compared to the sham. In the alpha, we cannot see any significant difference between the sham and PBM p-value. There's no significant changes. And alpha 2 similar. Delta 1 a little bit difference, but basically not very small changes here. Beta 2 is we can see those significant changes, very small changes. But in the beta 3, there is you can see there is no changes, small changes in sham. In the PBM, you can see a lot of changes in the stimulation area. This is the p-value, and this is the sham in PBM. In the PBM, we can see the significant gradual increase, especially in this stimulation area, frontal or central area. So continuous near infrared light make the EEG beta 3 rhythm increase during the stimulation, and remaining the beta 3 increases remain after the stimulation compared to the sham significantly. And this is the gamma. You can see gamma also you can see PBM, and this is the PBM changes and sham changes. You can see this difference in the statistical difference. You can see the gamma in the stimulation area, significant gradual increase compared to the sham. So we can see the significant changes in the stimulation area, and the decrease in the delta and theta, increase in beta 3 and gamma. This is very similar to previous study, and major changes increase in beta 3 and gamma. You can see beta 3 and gamma is changes very significantly compared to the sham. But this beta 3 and gamma changes related to the increased blood flow in that area. This is a very famous figure of the frequency of the EEG frequency and blood circulation relationship between the blood perfusion and EEG frequency. The blood flow is decreasing in the alpha band and increasing in beta and gamma band. So our result is the beta 3 and gamma is increasing. This is the beta 3 and gamma. Beta 3 and gamma increasing means the continuous PBM makes the brain rhythm, makes the blood circulation more increased blood circulation, I think. And the next part, I'd like to share the real-time EEG effect of the tPBM using pulsed near-infrared light. The experiment setting is very similar, but there are, however, the continuous PBM and pulsed PBM require a very large difference in experimental setting. For example, when operating PBM stimulator at 10 Hz, 10 Hz EMI, electromagnetic interference, appears in the EEG signal. So the pure EEG changes by the 10 Hz PBM and the EMI caused by 10 Hz LED driving current are superimposed on each other. So we need to separate them. So we devised the special signal processing process, which will be described in the next page. And first of all, the cumulative changes during PBM was calculated based on S1 data, not baseline data, because we need to remove EMI. The EMI only we can find from in the stimulation period. So to remove the we need to remove the EMI, and to see the pure PBM changes, we calculate all the EEG changes based on S1 data, not baseline data, and also to remove any EMI changes during the experiment. All experimental control was done remotely using the Bluetooth device interface. And as shown in the table, there are 16 sessions of 10 Hz PBM, 16 sessions of 20 Hz PBM, another 16 sessions of 40 Hz PBM, and another 16 sessions of sham stimulation. This experimental design is known only to the remote experimenter. The subject cannot know which PBM frequency or which PBM is being investigated. So the study design is single-blind, sham-controlled tPBM study. This is the very special signal processing process to eliminate the EMI generated by the PBM stimulator. During the PBM stimulation, this is the low signal of 15 minutes, the 10-minute stimulation. The 10-minute stimulation EEG data during the 10-minute stimulation is bandpass filtered with pulse frequency, EMI frequency. For example, we apply 10 Hz PBM, then 10 Hz bandpass filtered. 10 Hz bandpass filtered frequency is going to the AMICA process to reject the EMI component, and band stop filter, another band stop filter signal is going through and combined. Then we can find the EMI removed clean data during the stimulation period. And using this data, we can go through the statistical analysis. With statistical analysis was performed, the 48 PBM data and another 16 sham data. The statistical process is very similar in the continuous PBM study. This is the delta band changes during the PBM. This is the S2. All the calculation based on S1 data to remove the EMI data in EMI data, and we do the two different approach. One is the S1 based calculation. Another one is the special signal processing technique to remove the EMI component during the stimulation. This is the change in delta over the course of the PBM. We can see this is the 10 Hz minus sham, 12 Hz minus sham, and 40 Hz minus sham. This is the change during the S2, S3, S4, and this is the post after the stimulation. We can see this is the p-value map. The red area means the significant difference between the 10 Hz stimulation, real stimulation, and sham stimulation. I think the delta band, the change in PBM between sham and this multiple frequency does not seem as obvious. But let's look at the changes in zeta during the zeta band changes during the 10 Hz frontal stimulation and 20 Hz frontal stimulation and 40 Hz frontal stimulation. We can see the very strong increase in zeta at the 10 Hz frontal PBM and then disappeared. This does not appear in the 20 Hz or 40 Hz PBM in this in this stimulation period. 10 Hertz stimulus to the frontal area is a frequency that makes healthy adult sleepy. And 20 years stimulation did not produce a change in theta at the time of the stimulation, but increased theta in the right hemisphere after the stimulation ended. I think this result suggests 20 years stimulation may be overstimulating for those right hemisphere, and 40 Hertz stimulation did not produce any significant changes. So to wrap up, the 10 Hertz stimulation in the frontal area makes the subject more sleepy. So I think the theta band significantly increase in the frontal or central area, and the 20 years frontal stimulation makes no change in theta during the stimulation, but after the stimulation, there are increase in the right hemisphere theta. This means the 20 Hertz stimulation in the right hemisphere, not left hemisphere or central, right hemisphere, 20 Hertz is a kind of overstimulating, not the optimum frequency, I think. That's the theta band changes during the first PBM stimulation. And the alpha 1 band, you can see the frontal 10 Hertz PBM appear to have the increased alpha 1. And the 20 Hertz PBM also shown to increase alpha 1 over time. The 40 Hertz PBM does not show any significant changes. So we can think about why the 20 Hertz PBM makes the alpha 1 changes in this S4 and post stimulation, and we can go through all the frequency band and finally we can find the different stimulation frequency and the overall different effect. After we can make the view after going through all the frequency band. And in the alpha 2 band, this is the changes of the alpha 2 rhythm, and this is the p-value map. The 10 Hertz PBM appear to have some impact on alpha 2 band, like this. 20 Hertz PBM significantly affecting alpha 2 band as well, more than 10 Hertz PBM. 20 Hertz PBM significantly affecting the alpha 2 band, and 40 Hertz is also affecting a little bit. And the beta 1 band, the 10 Hertz PBM had some effect in beta 1, and for 20 Hertz and 40 Hertz, the 40 Hertz appear to have some effect here, but not so much in the beta 2 compared to alpha 2 and alpha 1, alpha 2, and beta. There is changes, and in the beta 2 band, there is no significant changes in the 10 Hertz PBM, but relatively large changes in 20 Hertz PBM. The small change is 40 Hertz PBM. And in the beta 3, you can see the strongest changes, we can see the after the 40 Hz frontal PBM, the beta 3 significantly strongest changes in the beta 3 band. There are still 10 Hz is some effect in beta 3 and 20 Hz a little effect in 20 Hz PBM, but the most significant result effect is in 40 Hz PBM. And in the gamma as well, very similar. Combine all of this. This is the 10 Hz changes compared to the sham, and 12 Hz PBM changes compared to the sham, and 40 Hz PBM compared to the sham. This is the p-value map. This could be rather complex, but we can see compared to the sham, the 10 Hz frontal PBM shows EEG shift from the theta to the beta 1. It's predominantly strongest effect shift in theta. And we speculate already that the effect seen in the slow theta, because the frontal 10 Hz can cause drowsiness. So the theta is enhanced. And the 20 Hz frontal PBM shows EEG shift from alpha 1 and alpha 2 and increase in the right hemisphere after the PBM stimulation. And also, they showed the 20 Hz, they showed beta 2 changes. Although it is a 20 Hz PBM, I think it is assumed to have effect of the shifting EEG in the direction of the 20 Hz shifting the EEG in the 20 Hz direction rather than just increasing 20 Hz. So it seems like that increase in alpha 2 could also alpha 2 is increased, alpha 1, alpha 2, and going to the beta 2. This kind of increase, not just increase in beta 2, there is this subject having the 10 Hz alpha peak frequency, the alpha rhythm going slightly faster, and the 20 Hz increased significantly in the 20 Hz PBM stimulation. And the 40 Hz frontal PBM, on the other hand, seem to increase, seem to initially decrease the gamma, but eventually increase the beta 3 and gamma significantly. So I'd like to
Dave,
discuss.
if I may interrupt 1 second, so just wanted to let you know we have 10 minutes. If you want also to leave time for question, and a quick question about the table before, because so that we all understand how to interpret. So this is a p-value table.
Right.
The directionality is linked to the color. So if it's green, it's an increase. Is that what it is?
You can see this is the 10 Hz PBM, the significant changes from the theta to beta 1, and 20 Hz PBM, we can find the significant changes from alpha 1 to beta 2, and the 40 Hz PBM, we can see the changes in beta 3 and gamma. So stimulation frequency, 10 Hz frequency and 20 Hz frequency stimulation, 40 Hz stimulation frequency makes the EEG spectra going to that direction. But the green color is the unexpected effect, is the green color. I think this is the very slow wave increase in the 20 Hz stimulation. This slow wave is the reflection of the overstimulating effect in this right hemisphere. Usually 20 Hz is too fast for the right hemisphere, so that's why this is a slow wave theta increase after the stimulation. And another unexpected result is the gamma wave decrease in the first stage of the stimulation. But finally, gamma increase, but during the course of the stimulation, gamma decrease. It is not an expected effect. Yes, but I'd like to discuss this result and wrap up the result in the next page. And this is the repeated measurement on a single subject. The interpretation is quite limited. For continuous PBM, we found significant changes in stimulation site in beta 3 and gamma, but pulsed PBM, we found significant changes in EEG occur mostly around the PBM stimulation frequency. So the pulsed PBM is showed more complex changes compared to the continuous PBM, but there is if there is no effect of frequency, we can only expect the changes beta 3 and gamma as with the continuous PBM. But pulsed PBM, we can see the significant changes in EEG around the PBM stimulation frequency. There are unexpected effects such as frontal 10 Hz interacting with the drowsiness with no changes at post-baseline, and frontal 20 Hz increasing theta in the right hemisphere at the post-baseline. This is the unexpected changes. It is likely that there are different effects depending on interaction between the frequency of PBM and location of the PBM, and the difference in the size of the PBM stimulation area, and difference in QEEG pattern of the PBM recipient, and difference in PBM stimulation time. There are many kinds of complex parameter effect together. So further research is basically warranted, and QEEG-guided individualized PBM protocol generally be recommended, and the pre and post comparison for specific PBM protocol will be more helpful finding optimizing protocol and monitoring PBM effect. The pulsed PBM could be tailored to have various QEEG effect compared to the continuous PBM. Basically, we can find the PBM pulse frequency PBM effect changes. We can find the changes in around the PBM pulse frequency. So we can tailor various QEEG effect using the pulse frequency. And so QEEG-guided pulse PBM would be the more effective and more safe future medicine. That's my discussion of the pulse PBM real-time changes result.
Thank you so much, Dave. Maybe we can take time for a few questions. I love the way you mapped the effects of PBM and different parameters on EEG. If you're done with the slides, you can bring that down so that we can see all the different participants can stop sharing. And I will just read the first question from Han Lee. What was the sample size, number of subjects for each group of stimulation case? And Han Lee, if you have more to add to this question, go ahead.
No, that's the quick question because we only have 5 minutes.
Yeah, basically, this is the subject is one single subject to the many different stimulation stimulation intervention. Sometimes sham intervention, sometimes the real stimulation. The single subject in the pulse frequency stimulation, there are 16 sessions of the sham stimulation, 16 another 3 different frequencies, 16 sessions of the pulse stimulation.
Got it. Thank you, because it's very complicated protocol you have. So I was just wondering how many people you have in order to create some of the conclusions. Thank you.
We focus one subject because the subject, different subject is another compounding factor. So we in this study we only used one subject and we applied very similar condition to compare to find the real pulse frequency effect.
Second question from Reza. Can you please confirm if the carryover effect was taken into account during the analysis? And Reza, welcome to elaborate.
Hello, Dr. Kim, and hello, everyone. Thank you for your interesting talk. So my question is, as I understand from your study design, you have different stimulation randomly for different days, right? And did you take into account the carryover effect of each stimulation on the second one, like the 10 hertz over 40 hertz or 40 hertz over 10 hertz?
I'd like to show the slide again. Please repeat the question again.
So in your study design, you have a random sequence of stimulation, right?
Yes.
And did you consider the carryover effect of the 10 hertz over 40 hertz or vice versa? Or 20 hertz?
This is the study design. So all the frequency or sham is the randomized.
Yeah.
So each session is separated enoughly. So I don't think the between session effect is not so much, I think.
Okay, thank you. Paulo, you are mute.
Yes, sorry. I was just saying that I didn't see all of you in case anyone else had any questions. I know we are at the end of the session already, but any comments or questions? You know, one comment I had was it's interesting the fact that Dave, you're noticing in between sessions different effects. And my understanding, if I understood correctly, so there was an experiment where you were crossing over to different parameters, but also, okay, there is that grid where you're presenting the data and you say, for the 10 hertz, for instance, you say session 1, session 2, session 3. Does that mean that in that experiment, they were in different days repeated sessions for the 10 hertz?
Basic one session is the 15 minutes.
Mhm.
So the S1, S2, S3, S4, combining S1, S1, S2, S3, S4 is 10 minutes. So 15 minutes is one experiment.
Oh, I see. So those S1, S2, S3, S4 were actually happening all within that administration, and they were kind of divided in those chunks.
Yes, because we want to tracking the change during the stimulation.
Makes sense. Makes sense. So you wanted to record in between. Totally.
Yes.
Thank you so much. This was quite some data and an interesting way of mapping the effects. Thanks for being here today. There is a question on the fly. I won't hold everyone, but if you want to stay, whoever wants to stay for the last question, a few minutes, welcome to do so. Go ahead with your question.
Yes, this is very interesting data in terms of surface EEG. I would be very interested to see what happens with tPBM when we look at connectivity data, QEEG data, including on SW Loretta or fMRI. And I'm wondering if there is any thought of looking at how this affects these metrics.
I also very interested. I'm very excited to see the connectivity pattern during the stimulation. In this study design, we only focus on this frontal area, but we can connect. We can select the two different brain area. Then we can find kind of connective changes between two different areas. And also, I did not show the connectivity changes in this study data. I can see what kind of connectivity changes during the frontal stimulation. As you saw, the frontal activation may have another activation, stimulate another area too. So that reflects kind of connectivity, interconnection effect inside the brain. So we only target the frontal stimulation, but there are kind of network effect too. But I did not show the network effect using this data. So I'd love to go into further the network effect.
Thank you. Thank you all. And thank you for coming, Dave, for this quite elaborate presentation that we enjoyed. And hope to see you all for the next session. Take care.
Take care. Thank you for your attention.
Thank you.
Thank you.